This video aims to demonstrate how Global Maritime's GM OPSIM program can be used to simulate operations of a crew transfer vessel working at an offshore wind farm. The program is a simulation tool which can be used to improve efficiency of current operations or at the project planning stage to assist decision making for aspects such as vessel selection or operation time frame, including necessary contingency plans and shift patterns. The starting point for any simulation is a time series of metocean data. In this case, the data is recorded for every 3 hours over a duration of 3 years. The scenario for the simulation in this video is for the maintenance of 3 turbines, each requiring 30 hours of work. The turbines will be maintained by 3 teams, taken from the port to each turbine by the CTV. A range of limitations are modelled in the simulation. These are based on limiting weather conditions for sailing and for crew transfer from vessel to turbines. A further restriction is that operations must occur in daylight, with shift duration not exceeding 12 hours. Let us start by looking at the limitations imposed on the transfer of crew between vessel and turbine. This limitation is based on directionality. That is to say that the limiting HS for connecting to the turbine fenders, and therefore for crew transfer to occur, varies based on the wave directions relative to the turbine. For instance, in head seas, the limiting HS for crew transfer is 1 metre, compared to 2.5 metres for following seas. Limitations based on tide, current direction could also be imposed if required. The second limitation is for the maximum allowable weather conditions in which the vessel can sail. One fixed limit of 3 metre HS and 25 knots wind speed has been set here. But, if required, a range of varying sailing limits can be analysed. Lastly, the limitation of daylight-only operations is set. The time of day, month and year is based on the metocean time series, and the hours of daylight are calculated based on the user-specified latitude and longitude. Forecasting is then used to ensure the operational limits are satisfied. A sailing forecast is set, ensuring that the vessel will not leave port unless the forecast for the next hour satisfies the weather limits for both sailing and crew transfer. Similarly, sailing back to port is controlled by a forecast. This is a last chance forecast based on daylight hours and sailing limits. This means that the vessel looks for the last available 2-hour window during which sailing and turbine transfer limits will be satisfied during daylight hours, and initiates the pickup of crew and return to port at the start of this window. Finally, to ensure that crew is not dropped off at turbines without the possibility of being picked up again, the drop-off operation is also linked to the return forecast. That is to say, that if prior to a drop-off a 2-hour window for pickup is not available within the next 12 hours, drop-off will not occur. As mentioned earlier, 30 hours of maintenance work is scheduled for each turbine. From the moment crew has been dropped off onto a turbine, a counter clocks the amount of time the crew is spending on this turbine. Once pickup occurs, the time spent working is transferred to the work done counter. Drop-off at this turbine will continue until the work done counter reaches 30 hours. For the purposes of this demonstration, we have analysed 2 turbine fender orientations, thus allowing us to assess which orientation will lead to the lowest number of days required to complete the maintenance schedule. The turbine orientation will of course affect the drop-off limits, which are based on wave directions relative to the turbine orientation. The simulation can then be played through with varying speeds. As we can see, the simulation starts at night. The vessel is in port, and as expected, no crew is present on any turbine. Once daylight hours are reached, the vessel sets off, as the HS and wind speed limits are below the limits for both sailing and turbine drop-off. Once drop-off has occurred at all 3 turbines, the vessel goes to the layup area, where it remains until the last chance forecast triggers pickup operations. Here, the limiting factor is the daylight hours remaining. Once the number of daylight hours remaining is less than 1, the vessel sets off for pickup. As can be seen, no operations occur in day 2, as the operational limits are never satisfied. All the maintenance required for turbine 1 is completed after day 4. Therefore, on day 5, the vessel does not stop at turbine 1. Once all the turbines have been maintained, the simulation finishes and restarts at a different time instant in the metocean data. This can either be set to be at a specified interval, or to carry out the simulation for every possible starting point in the meta-ocean time series, which would increase the number of simulations and statistical accuracy of the results. Once the simulation is run, a number of post-processing reports are available. For this simulation, we will obtain the mean duration of a scheduled maintenance based on the time of year in which the maintenance is undertaken. As expected, the required time to complete the maintenance is lowest during the summer months. The results for all the scenarios run, so in this case the 2 turbine fender orientations, are automatically generated. Another useful output which can be produced for project planning is a monthly breakdown of the hours a vessel can spend out in the field. This is shown here. This video has demonstrated some of the basic capabilities of Global Maritime's simulation tool GM OPSIM, using a simple and generic example. The program can be readily customized to provide any required statistical results and predictions for a vast range of operations which can be modeled to occur simultaneously, and for wind farms of any size.